videos of the panelists pinned up. Okay, so so while that's being done, let me just introduce the panel. So we have a great panel with okay, so we have so all three people in the panel work on on cryptography and on protocols. So let me start with Zvika, who's shown up already. He works on fully homomorphic encryption. He's made it his I guess mission to make FHE easy, efficient, and easy to use. He's also worked on quantum aspects. I guess we have joint papers on tests of quantumness and certifiable quantum random number generation, and he also has worked on quantum garbled circuits. Our other panelist is Anne Broadbent, who's from the University of Ottawa. So Anne's worked on a number of aspects of quantum cryptography. I'll just mention a few that have been particularly influential. She has this paper on universal blind quantum computation, which was particularly influential in delegated quantum computing, and she's worked a lot on issues of having to do with quantum zero knowledge, and on issues of composability of quantum protocols. And our third panelist is Yael Kalai, who's a senior researcher at Microsoft Research in New England, as well as an adjunct professor at MIT. So in addition to all the work on cryptography, she's also worked on delegated computation, including this very nice paper on interactive computation for muggles. I guess I really got, so one of the first papers on having to do with, this border between quantum and crypto was her paper with Ran Raz on the power of no signaling proofs. So let's start the panel with maybe 3 to 4 minute minutes for each panelist to comment on the talk, as well as more generally on this intersection of quantum and crypto. So starting with, please, anybody?
I'll start.
Okay.
Because you guys are quiet. Zvika, did you want to start? Were you about to unmute?
Let's hear you first.
Okay, because I've been waiting a long time to say this. First, for me, the talk was unbelievable. It was a real pleasure. I sat here, I had a great time. So thank you. And I learned a lot. But it got me thinking, especially in the beginning of your talk, which is, we build cryptography, which has traditionally been classical. And it's clear that we need to upgrade. And the question is, how do we do it? And as you said, okay, move to LWE, that's one way, or just move to post-quantum secure assumptions, but clearly that's not enough. And one thing that you talked about is you say, well, now go to all your techniques and make sure you don't use rewinding. Or if you use rewinding, make sure that it's compatible, that you can rewind a quantum adversary. But actually, I'm not sure that's enough. I mean, clearly you did you did a non-black box dive into the Killian protocol. But let me explain what kind of got me thinking in your talk. Actually, classically, I can prove that the Killian protocol is sound with only 2 rewindings. I don't need polynomial linear rewindings. And let me tell you my proof. In my proof, I'm going to generate I'll rewind twice. Hopefully, I'll get some intersection in the PCP queries. And I'm hoping to get a collision. Now, if I get a collision with non-negligible probability, I won. If it's negligible, then in the analysis, then I want to say, well, if it's negligible, then I essentially I'm going to say if X is not in the language, it cannot be negligible. But that's kind of the proof. So in other words, the reduction in the way I can think of Killian, my reduction only rewinds twice. Why the rewinding succeeds, in the proof of why the rewinding succeeds, I'm going to quote unquote rewind many times. So even if the reduction only rewinds twice, it may work. I don't know. It's a thought-provoking question. It may work for classical and may not work for quantum. I don't know. It's anyway. I want to have a conversation around this. I think it's a kind of a basic question in general for upgrading crypto to post-quantum crypto.
Umesh, can I respond or should we continue?
Yeah, please do. In this case, yeah, go ahead.
Yeah, great. So I think you're talking specifically about like the Barak-Goldreich proof strategy because this proof is, I think, Barak-Goldreich that you can do Killian with 2 rewinds, 1 rewind actually, right?
Right, exactly.
I think my perspective on this is that mechanically what the proof is doing is it's only rewinding once. But the reason that you can show that rewinding once suffices to find a collision is only because you can have this thought experiment where you're actually rewinding many, many times. And you use the fact that because rewinding many, many times works, this necessarily implies, because classical trials are independent, that something will happen when you only do 1 trial. And so since all of this is a sort of a thought experiment anyway, like I guess I don't see the huge distinction between like, well, I'm only mechanically going to rewind once and then appeal to like a thought experiment where I rewind 1,000,000 times. And just saying like, actually that reduction is not really rewinding just once, right? Like when you want to phrase that as something that you want to do for a classical attacker or for a quantum attacker, then truly like what you're using about the attacker is the ability to query it many times. And like that's why the Barak-Goldreich proof strategy doesn't actually help you prove the post-quantum security of Killian. I guess it's like maybe my answer is that it's kind of a matter of opinion of how much that reduction is actually rewinding, because maybe it only does it once, but if it's relying on the fact that something would happen because you could rewind it many times, and it's not clear to me, it's only a 1 rewind reduction.
So in other words, I guess my point is, if I give you a proof that it's classical proof, and in my classical proof, I rewind only constant number of times. And let's say I also have some way using Unru's technique to take any such protocol, make it post-quantum. Because if it's only constant number of rewinds, we have ways to easier ways, I think black box almost ways to upgrade our protocols to be post-quantum rewind. But that's not enough. Because exactly you're saying, well, in their case, maybe in actually what's going on in the proof, they do rewind. So I guess my question is, do we have a black box way, or is there any hope of having a black box way, like a general technique of saying, look, if you have a classical proof, it rewinds constant number of times, we can take it generically and make it post-quantum. Is there any hope, or is that kind of meaningless because in the classical world, we do rewinding in our analysis in some sense?
Yeah, I mean, I think a lot of it would depend on like rewinding is such a nebulous term, right? Like it's unclear what we mean when we say rewind. And maybe like this like is Barak-Goldreich really rewinding once or not? Like that's sort of a matter of how are you defining the term? And so maybe like at such a broad level, it's hard to say if there would be an answer, but that's why I was saying in this talk, I want rewinding to mean this particular thing, write down this many transcripts. And in that setting, like, this technique is a black box way to lift classical proofs to the quantum setting, provided you have some sort of collapsing style guarantee. Maybe I'll leave it there and let other panelists.
Yeah, just to, so I guess, Yael, you were saying, if I understand right, you were saying, well, how would you know, if you had a protocol which rewound only a constant number of times, how would you know that you should use much heavier prove quantum security? How would you even know that somewhere in there wasn't something lurking?
Exactly.
That's the question. Okay.
Exactly.
And may I ask another question? So I didn't completely follow. So how this reduction to 1 or 2 rewinds work? So shouldn't that require that your error probability was very small, and you were able to your quantum technique was able to work with those small error probabilities? So is that where the Unruh technique breaks down? So he deals with a constant number of rewinds, but then why? Okay, so is that where it why it can't be applied with this kind of proof?
I have to say I am not sure Unruh's technique cannot be I'm not sure Unruh's technique cannot be used if so suppose all you want to prove is that Kilian, you can't cheat with probability 1 minus epsilon. That's all you want. That's all you care about. And if you have that, you're happy, because then you can repeat and so on. So if all you want is that you can't cheat Kilian with probability 1 minus epsilon, I'm not 100% sure that you can't use something simpler. Of course, I'm not going to get the result. They won't give you the result that they give, which is just the 4-message Kilian. But it's not clear to me that that's not possible.
Oh, I think that what's going to happen, though, is you're going to have such a terrible soundness error that your sequential repetitions will lose the succinctness.
Okay, I'm not sure, because there's only one rewinding. It's not. I don't know. I'm confused about this issue. I have to say.
So it's going to be like 1 over witness length or something. This is what you're saying, the soundness gap. So you have to sort of do it witness number of times in order for.
Oh, I mean, the soundness gap is actually going to be really terrible. It's going to be 1 over PCP length, actually, because what you need to do is be able to invoke gentle measurement enough times. The proposal, right, is to use gentle measurement to just keep rewinding, and that works as long as your prover was succeeding with probability really, really close to 1. But for this gentle measurement, you're going to have to measure something like PCP number of times. Actually, maybe much worse, because PCP number of times is how many accepting transcripts you need. But there's also the blow up of the failing transcripts. And so it's going to be much worse than that. And then you'll lose the succinctness when you sequentially repeat.
But that's if you want to, because you're trying to get an entire PCP. But why? You don't need to get an entire PCP. All you need is to find a collision. You're working hard because you want to find a PCP, right? You're saying, aha, look, you can't have a PCP because X is not a language. How can I have why are you working so hard to find a PCP? I have X not a language. All I want is a collision. I'm going to wind once, and to wind once, it's enough to, to have 1 minus epsilon. 1 epsilon is not too bad. I'm being provocative. I don't know if it works, but I'm trying, it's not clear to me that it doesn't. It's not clear to me that you have to work so hard. We don't need your PCP. All I want is a collision. I'm trying to, have a reduction, not the.
If I can, do you mind if I interrupt? So there is a PCP appearing also in this Goldreich proof, right? It is the way that you argue that the thing is sound is you say, okay, the reduction can't find the PCP, but there exists a PCP that could be there. Whereas in the quantum setting, the adversary is not even a function. Right. In the classical setting, you can say the adversary is a function from challenges to answers. And so the PCP is contained in this function in some way. In the quantum setting, this is not true. The way the adversary behaves depends on the order in which you query things. Because, non-commuting and stuff like that. So I think this is sort of the conceptual problem. And so any proof, any cryptographic proof that relies on the adversary being a function might run into this kind of problem.
But the adversary is sort of a function. You can always think about this sort of density matrix of the state of the adversary, and this actually has a classical description, and this sort of completely sort of characterizes the adversary. What happens if you ask it a query, any query that you want at the first query, any query that you want in the second query, and so on. So, is it about a function existing or having access to it? Because in some sense, it does sort of exist so long as there is a
function. Do we next message function?
Yeah, even the next message function, you can define,
but then it's not a function of its input anymore.
You can rewind, right? You can rewind or duplicate the state or all these things that you cannot actually do in actuality, but these things do exist. It's like the probability that the adversary answers correctly on some, or some measurement outcome is something. This is sort of well defined, given an adversarial state. You just don't know how to access it. So in a sense, it is possible that the adversary that you can given the density matrix of the adversarial state, it does somehow define a PCP, but we want an efficient reduction. I mean, because it's a computational assumption, then you want an efficient reduction. So this is well, the obstacle. I guess maybe I'm just nitpicking on a minor point.
Yeah. No, so these, I guess, good questions. I guess these things get pretty delicate. So it would be very interesting to see whether one can make this, some simpler proof work. But there are a lot of obstacles along the way, I think. So, great points. So, can we? Zvika or Anne, would you like to go next?
Sure, I can go next. So thanks a lot, Fermi. Let me echo the compliments that we heard already. I have 3 questions going from maybe more concrete to maybe kind of abstract and funny, crazy, I don't know. So the first concrete question, and maybe this is along the lines of what Yael was saying, or maybe you said it and it's just so basic. So why did you, okay, so you're really opening up the proof of the Colloquium protocol and looking to get the transcripts. I mean, that was looking to record the responses. That was your disclaimer on slide 31. What if instead we looked at the entire protocol as a quantum process, and wanting, like, all you want is one outcome at the end, like accept, reject, or maybe a transcript, or I'm not sure exactly what, or maybe some input state that is contradiction or something. Why can't we just do the entire thing quantumly and then put, like, we want that event and then amplify using a watches recording, like kind of, or watches rewinding, like another type of process?
Yeah, good. I think I see what you're getting at. I guess that maybe the difficulty I'm seeing there is, like, what is the event going to be? I can purify the whole process, like leave everything in superposition, have an adversary state, only measure if the verifier is convinced, never measure anything. But now I need to define some event to make what you're saying go through. Right? I don't see what the event would be.
Is there a predicate, like you had a collision or a PCP or something like that?
Yeah, but the collision predicate is hard to define because that's sort of like over 2 executions. Like if over 1 execution, I can't sort of compute this collision predicate. There's no notion of a collision on a single execution.
Goes back to the hypothetical experiment that you could do.
Yeah, I guess all I'm saying is, I can run the whole adversary quantumly, compute anything I want about its responses. But the thing I cannot compute about its responses is, like, is there a collision? Because the collisions are across 2 different invocations. And that's where the difficulty comes in.
Okay. So another question is so it's really interesting when we get to these quantum challenges. The heart of it is the no cloning theorem and issues like, well, you can't clone, therefore you can't keep an initial state, or you can't keep a transcript and whatnot. And then I found that often when we were forced to think with a no cloning mindset, we were forced to rethink the original definitions. Actually, what do they really mean? So this happens in things like semantic security. I'm sure other ones too. So I was wondering, from that point of view, is there something that you learned that you wanted to share of what is rewinding, what is a transcript, what was Colloquium's protocol actually doing at the heart of it?
Yeah. Okay. I think I understand your question, and maybe I'm going to give an answer that's a little orthogonal to it, but it's just something that I learned about cloning. Sort of in the early stages of this project, we were thinking, well, the goal is to write down a PCP, right? So, just write down any valid PCP. So if that's the goal, then sure, we're allowed to clone the state. You can write down the PCP inefficiently too. It's fine. But then the problem you run into there, this is like a really natural thing you might try if you're faced with this question of trying to prove security of Killian, right? Just, you know, the problem seems to be cloning, but if you're trying to get something information theoretic, just clone anyway. The problem with that argument is that it doesn't work. And the reason is that when you just arbitrarily clone the prover state, you won't be able to appeal to the computational assumptions anymore. And once you lose the ability to appeal to computational assumptions because you've cheated and used cloning, then you can no longer guarantee that the responses you record are going to be consistent. So it's not clear that you get a PCP now. And so like one thing that was useful to think about like the early stages for sort of like testing the different ideas we had was just consider always the prover who's just going to commit to uniform superposition of all PCP strings. And you'd better come up with a strategy that's actually going to narrow this uniform superposition down to a single PCP string. And like it was sort of helpful to think about this, that like, you know, if the prover committed to a uniform superposition of strings, and I extract one chunk of one random string and one chunk of a different random string, it's really useless for me is trying to get a reduction. And for the other question of, you know, do we learn anything new about like security guarantees? Maybe in this particular setting, I'm not sure if like any of the security definitions like ought to change, because like what we want here is really, we want the classical definition. We want that a verifier cannot be convinced. And the only thing we want is, we want this extra property that like, also if you have a quantum computer, you can't convince me. So for that reasoning, I guess I don't see, you know, any reason to sort of change the definition other than ask for security against quantum adversaries. But I think definitely when you have more like inherently quantum functionalities, which Killian is not, like that's when that question is like much more meaningful.
Okay, thanks. Yeah, my final one, maybe there's nothing to say really, but I was wondering if there's links with non-local games, just because when you had the Merkle tree at some point in the commitments, it looks like you could maybe reinforce this this commitment idea with separation of different parties. And you could like test the PCP with multiple parties. I guess probably people have done this before. So yeah, did that come up or?
Yeah, it came up, absolutely.
Okay.
Yeah, it came up, and actually like Yael might be more qualified to speak about this because she has a paper on this sort of connection. But like one thing that we realized during this project was that like this Killian protocol is this like this 4-message protocol. So one question response, one question response. And it turns out that if you use like the, maybe I'll help me with this if I screw this up, but if you use like the right hash function in Killian, if you replace the collision resistant hash function with an appropriate so-called like statistically binding hash function that like binds to a few positions, basically what's happening is what you can imagine is the Killian protocol is actually doing the same protocol twice. Like it's asking some PCP questions and getting answers, and then asking PCP questions and getting answers. But the first time you do it, it's encrypted. Like there's this new perspective of Killian's protocol that you get from plugging in a particular hash function that you might want to plug in to prove quantum security. And what turns out to be the case is that the first 2 messages are actually a known protocol, this like BMW heuristic that Kalai and Rothblum proved secure for these no signaling PCPs. So this is like protection we realized early on, and then like, well, it doesn't, we get stuck at polynomial time computation with this. It's a limitation of this particular approach. But that is one way that you know, these non-local games show up somehow in these protocols in this analysis. Now, did I return any of that? Sorry?
I just want to say I'm impressed with how well you understand that protocol. Okay.
Awesome. I'm glad I asked. Thanks.
Great. Thanks, Anne. So, Zvika, do you have any comments?
Yeah. So, I mean, I think I probably voiced myself enough. But just yeah. Again, also I wanted to thank Fermi for the enlightening talk. And maybe sort of, okay, I have 2 things. One is to sort of go back to the beginning and sort of really emphasize this point that Fermi was making, that sort of thinking about sort of classical crypto against quantum adversaries is more than just sort of replacing factoring with some sort of quantum resilient problem. And we really sort of need to go back and look at our definitions. And this is sort of an ongoing process and then I guess there's a lot of contributions by Anne, by others, to sort of trying to understand what are the right ways to formalize our cryptographic notions in the quantum setting. And I think there's still sort of work to be done there. You're like, okay, what happens if it's a protocol? What happens if there's rewinding? What happens if this? I mean, I don't know that we still sort of have the complete picture of how we should think about sort of modeling cryptography in a quantum world. So this is sort of, I guess, sort of an open-ended thing. And I don't know, perhaps, I don't know if it's related or not, but I guess my question to Fermi is like, what are the sort of limitations of this techniques? Is there like somewhere where you want to take it and it doesn't work? I don't know, like if the verifier has secret randomness or things of this sort, does it, what would you say is, well, the next challenge or maybe like even broader, what will be a broader version of a result of the form that you were talking about?
Thanks, Zvika. That's a great question. I think you gave a great answer too. It's like, yeah, one of the really big next steps would be what happens if the protocol is not publicly verifiable, and it's sort of inherent for all of this because okay, maybe it wasn't clear in this talk where I'm using this property, but throughout all of this, I want to say that like anything that the security reduction could do, the adversary could do too. I'm sort of using this crucially to say that therefore the security reduction can't break assumptions, can't break collapsing, blah, blah, blah. So yeah, all bets are off when you have a privately verifiable protocol, because now even like estimating success probability or even before that, just seeing if you convince the verifier is hard. But like every part of this technique seems to like fundamentally rely on having public verifiability. And so one place where we'd really like to maybe use these techniques and try to understand security would be the Mahada Protocol, right? Where it seems like a protocol is sort of ripe for this kind of analysis, right? It's a protocol where you want to use parallel repetition. It's already has the collapsing property in some sense. And yet it doesn't apply because the protocol isn't publicly verifiable. So that's one thing where, it'd be nice to see if there's any connections, but it's unclear at the moment.
So sorry, what's the connection between parallel repetition property and the rewinding? Is there, like if you could do rewinding, if you could do like your technique for verifiers with which are not publicly verifiable, then you would be able to also get parallel repetition. Is there a connection there or formal?
Oh yeah. So one consequence of this work is that like parallel repetition for publicly verifiable collapsing protocols just works as you want it to. Like you can take like GMW, instantiate the commitments with quantumly binding commitments, and you can prove the parallel repetition soundness is what you want it to be. Using this rewinding technique. And it's it's sort of unclear how, if you can say anything like that when they're privately verifiable.
Okay.
Sorry, I think what I'm saying like makes it sound very like crazy. This is doable, but if you really stare at it, I think it's like maybe strictly easier than proving Killian's result.
So Vinod has a question.
Hi, Fermi. The question I have is, how general is a class of publicly verifiable protocols that your proof applies to? So you just said, if I understand right, that there is an example of a privately verifiable protocol where your techniques wouldn't apply, and that's Urmila's protocol. But how general? Do you capture all publicly verifiable protocols, for example, or?
Good, great question. Maybe this wasn't an earlier draft of the paper, and because I checked recently and it's not there for some reason. But we kind of did try to characterize a class of protocols we could handle. And the characteristics you need are first that the security is argued by rewinding one round. So one thing we didn't do in this paper is is just to prove that like IOP version of Killian is sound. Like that's actually open. Like we have not tried super hard, but it is like a sort of natural thing you might want to prove. And it might be pretty easy. You really have not looked at it. So first off, there's like a round restriction. Like it needs to be a question answer round, and that should be it. Maybe some rounds before it, but second restriction, publicly verifiable. Third restriction, it needs to have this collapsing property, and that property can be weakened a little bit. The way I phrase it today is that, you know, the adversary can't tell. The adversary thinks that when you measure its answer, that actually a binary output measurement was performed on its state. Right? I was saying this was crucial. But you can imagine a weaker version of collapsing that says that it can't tell if a polynomial output measurement was applied to the state. Like there's sort of maybe no reason to restrict to just 2 output measurements. It turns out that this technique can handle the disturbance from a poly outcome measurement applied to its state. So you can imagine like a definition of like weakly collapsing that says that the full measurement looks like a not too disturbing measurement. You can handle that too.
So out of the last 2 restrictions, which of them is inherent, do you think? Because Urmila's protocol, if I understand right, is neither collapsing nor publicly verifiable. Right? Maybe I'm missing something.
The hash function is collapsing.
It's collapsing.
Yeah, it's implied by the fact that it's indistinguishable from the injective mode. In the injective mode, you can measure. And so if it looks like the injective mode,
so it really is publicly verifiable. Thanks.
Yeah, sorry, there's one more condition. And the last condition is that it has to have some kind of like special soundness property. Like that's what the proof is doing. It's generating a lot of transcripts.
Right.
But the key thing though, is that you have to be like, to phrase this well, you should generalize special soundness a little bit, because Killian's protocol is not special sound. Right? Like think about the definition of special soundness. It says any collection of transcripts with different challenges will be enough to break soundness, right? But with Killian's protocol, I can give you a whole bunch of transcripts that only open a small fraction of the PCP, and that's useless.
Right.
But what you need is actually this like sort of average case notion of special soundness that says that, like, you know, if I send this adversary a whole bunch of random strings and it gives me correct answers on a non-trivial fraction of them, then I can break the soundness. And that's the notion of soundness that Killian satisfies, and this generalizes standard special soundness. And I think that's basically the limit of what this technique gives you.
Okay, thanks.
Great. You know, I think we are just about at the end of the time for the panel. Are there any other comments that anyone wants to make quickly? Anybody on the panel? Okay, great. Well, thanks very much. Thanks, Fermi, for a great talk, and thanks, Yael, Zvika, and for wonderful comments. And thank you for being here.
Thank you, Umesh. This was really, really great. For me, it was wonderful. Really, I had a great time.
Thanks everyone for coming. This was fun.
Thank you very much for the organizers and the speaker.
Yeah.
Great.
Bye, guys. See you. Bye.